Invasive computing is a novel programming paradigm allowing a programmer to specify the type and number of processors to be reserved exclusively for the parallel execution of a program. This not only helps to increase the performance but rather ensures the predictability and thus guarantees of timing, safety, and security properties, as the following demonstration of a distributed real-time control of an inverted pendulum shall show. In order to ensure controllability of the inverted pendulum, a standard video camera output delivering a new image frame exactly every 20th of a second has to be processed no slower than this time by 3 algorithms, starting with a computation-intensive color segmentation algorithm for detecting green and the red color text mounted to the pendulum, followed by a bounding box computation algorithm from which the pendulum positions are determined, and finally a PID control algorithm that controls the motor position on the rod. In the following, we show an invasive program that claims exclusive resources for each of these 3 algorithms in order to satisfy strict real-time requirements on an invasive multi-core architecture with 4 so-called tiles of resources. In our demonstrator, this invasive multi-core architecture is implemented physically inside an FPGA-based rapid prototyping system also shown. The invasion starts from the main program running on the upper left tile. For executing the 2 image processing algorithms, a tile called TCPA, lower right, is invaded together with an I/O tile to which the camera is mounted as well as the pulse width modulated signals of the engine control, upper right. The time-critical control loop then begins with a wait statement for an interrupted coming from the I/O tile, issued by the Digital Video Interface (DVI) of the camera and signaling that a new frame is available to be processed. In the next step, a so-called infect command initiates the parallel execution of the color segmentation and bounding box algorithms on the invaded TCPA. This command is therefore passed to the TCPA tile. Their execution, in turn, starts by fetching the image frame to be processed from the I/O tile. Then, the 2 algorithms are processed. The infect terminates once the computed bounding box results have been communicated back to the main program. In step 4, the main program calculates the current position and angle of the pendulum and calls an infect of the I/O tile to execute the PID controller using these values. Step 5. The control loop terminates by the main program returning to step 2 and waiting for the next image frame to arrive from the camera. The hard real-time criticality of this application program is obvious. If just a single frame, that is a bound of 20 milliseconds on overall processing time, is missed by processing the main control loop too slow, the pendulum is not controllable anymore. The same effect results if we interrupt a single source of more than this tiny time interval. In the following, we show the opportunities of invasive computing to also ensure safety properties of parallel programs. Another source of the incorrect behavior of our pendulum, apart from missing time deadlines, is the case of errors occurring during the execution of the program. Here, even a single bit error may affect the correctness of the computed position of the red pendulum marker and lead the pendulum again to become out of control, as the following clip illustrates. Here, we randomly inject bit errors in the memory of the processors that are responsible for the bounding box computations. The error injection is started here by a buzzer. As can be seen, the controllability is again impaired, this time due to wrongly computed pendulum positions, leading to wrong control values. As a remedy, the invading program may claim a replica row of processors, or even a second replica. These schemes of replication are also known as dual modular redundancy, DMR, or triple modular redundancy, TMR. As the replicas simultaneously execute the bounding box algorithm through infection, a single error may therefore be at least detected in case of DMR. In case of TMR, a single error may even be compensated by outputting the majority of the 3 individual results to the controller. Let's look how this works. With the same control loop, We invade a triple modular redundancy replication of the bounding box computation algorithm. Again, at some point of time, we start the fault injection. As can be seen, controllability is maintained under the assumption that no more than one row of processors is subject to an arbitrary bit error during the time interval of one bounding box computation. Finally, we showcased that security properties of programs may be enforced through invasive computing. One important security property is confidentiality. It might be harmful, for example, in case an attacker would be able to copy a program or data. To ensure confidentiality of application code and data, a lightweight encryption is realized by invading an encryption unit. Here, all data leaving the CPU is encrypted before being written to memory. Similarly, all data from memory is decrypted upon reads.
The previous demonstration was meant to show that invasive computing can be an enabler for the satisfaction of even strict, but definitely individual timing, safety, and security requirements of parallel programs. Contrary to how conventional computers operate today, in invasive computing, the computer acts as the advocate of the application program rather than the program obeying the goals of the machine. We do believe that this fundamental change in paradigm may propel multi-core technology for a myriad of embedded and cyber-physical system applications in the near future.